So thank you very much for attending this presentation. So my name is Javier Martinez, and I'm working at Thrustme on the development of space propulsion systems. So more specifically on everything which is related to iodine in the system, so on the fluid dynamics and on the thermochemistry aspects. So during this presentation, I wanted to introduce the work that we have done on the development of the I-25 cold gas thruster for the Robusta 3 emissions. So the main characteristics or the main challenges of this development was that it's a special version of the I-25 which has a tilted nozzle because the mission was planned before the thruster was planned to be integrated on it. So it's this decision came after the initial development of the mission. So the thruster, as I will explain after, needed to be placed in a specific part of the system. So this mission, the Robusta 3 mission, it's a mission developed by the Montpellier Space Center with funding from the Van Allen Foundation and from the French Aerospace Agency, which has several aims. So the main ones are three. So of course the scientific aspects of the mission, which are related to meteorology. So in order to perform precise weather and climate modeling, which is something that lacks right now because there are not so many measures which are done on the sea. So most of the measurements are done on ground-based stations and depend on the GNSS measurements. So the objectives are related to the estimation of the vapor content in the troposphere, which will allow to improve and to detect some meteorology phenomena like the one which is displayed on the image on the coasts of France and Spain. But it has also other objectives. So it provides a platform for students in order to be integrated on the development of a space mission, which is something very important in small satellite missions, and it also serves as a platform for technology demonstration. So as the case of the I-25 with the tilted nozzle, but also several other payloads that I will present to you later. So usually the choice of propulsion systems for small spacecraft depends on several constraints. So these constraints can be related to the mission. So for instance, the orbital maneuvers which are necessary, if it's necessary to perform a deorbiting or formation flying or some precise pointings or distances between spacecraft, or they can be related to space or to constraints on mass or other constraints on the spacecraft. And of course, depending on the parameters that want to be optimized, the choice will be one or other kind of propulsion system. So as you can see in the figure, we developed two kinds of propulsion systems. So the electric grid ion thruster, which is the MPT-30, and the I-25, which is a cold gas thrusters, and they have quite different characteristics. So in the case of the I-25, both the thrust and the specific impulse are relatively low, but this is compensated by the fact that using iodine has a very high impulse density, as I will explain later. In the case of the MPT-30, which is an electric propulsion systems, usually these systems have a very high speed at the exit, so very high specific impulse. And you can see in the table a comparison between the different or some typical numbers for small spacecraft propulsion systems, which are very different among them. So in the case of the I-25, the thrust is around 0.2 millinewton in a nominal mode, within a specific impulse which is around 75 newton seconds. So as I said before, the spacecraft serves as a platform for integrating several technology demonstrations payloads. So you can see in the table some of them. So of course the tilted propulsion system, which is displayed here, but also several other payloads that improve, for example, the solar panel hinges. So the one which is developed by Glix Industries, or the payloads which are related to the boards, thermal knives, or the harnessing of the spacecraft in order to to investigate technologies which are already used in the aeronautical sector. So why then using iodine for these kind of propulsion systems? So it's relatively recent, the development of or the use of iodine in propulsion systems. So the first time that an iodine thruster flew in space was precisely the I-25 last year on November, which I will explain later. But even the development of these systems is relatively recent. So iodine has some advantages, such as very high density, so it's stored as a solid, and it has a moderate vapor pressure, which means that it's relatively easy to produce a pressure in the tank that it's enough in order to accelerate this flow and to produce the necessary mass flow rates and the speeds at the exit. But at the same time, this pressure is not high enough in order to require pressurization requirements. So it can be typically 6,000 Pascal at 100 degrees. So it doesn't cause problems with handling or with the development of specific structures for holding it. However, it has some challenges as well, of course. So the main one is that it's a halogen, so it has quite high electronegativity, and this means that it has tendency to react with some substances commonly found in spacecraft. So mostly with some metals, and this is something that it needs to be studied and that we try to characterize by performing several corrosion testing campaigns, and by selecting some specific materials, especially for the wet parts of the thruster. And of course, something which is very useful in the case of electric propulsion systems, but which is the main drawback in the case of cold gas thrusters, is that it's a substance which has a very high atomic weight. So actually what this means is that the speed at the exit, or the theoretical speed at the exit that you can attain with iodine, is relatively low. But this is by far compensated by the fact that the impulse density, so this specific impulse multiplied by the density of storage, is extremely high. So it's even higher than in the case of lighter substances that of course produce much higher speeds at the exit, but of course the density is much lower, such as the case of hydrogen or lighter substances, or light substances, I mean. Well, and another advantage as well, it's that it's non-conductive. So even if some monolayers deposit on the exit walls of the thruster, this won't create problems for electronic equipment or for problems of charging in the spacecraft. So basically, the thruster can be divided in two main parts. So the first part is the part which is related to the storage of the propellant of solid iodine, and the thermal management system, whose objective is to sublimate this propellant. So in this part, the physics are mainly related to heat change processes, to phase change processes, and to heat transfer. And the flows are very low speed, relatively high pressure flows, even if the pressures, as I said before, they are relatively low in the case of iodine. And the second part of the system, which is basically the acceleration nozzle, and which expands to vacuum. It's a part in which the fluid gains velocity and the pressure becomes lower and lower. So the physics are quite different, so you cannot study this problem with the Navier-Stokes typical equations, and you need to use other kind of slip flow corrections to these equations, or even verify flows like direct simulation Monte Carlo simulations, or other kind of more specific studies of the plume and of the characteristics of the expansion into vacuum. So in order to qualify the thruster and to analyze the mass flow rates and the thrust produced by the system, we have performed several tens of cycles. So in the image on the right, you can see two of these cycles in which the stability of the flows was drifted less than 5%. And this shows as well the heating and the cooling down process, which is cooled down naturally in the chamber. But of course, we needed to measure as well the process in the long-term run. So we perform a lifetime test, which is shown here on the left, and it shows 44 hours of continuous mass flow rate and thrust measurements. And you can see that the stability of the mass flow rate during the whole process, it's shown in the figure. It was very stable during the whole lifetime testing. And of course, to analyze the thrust measurements, we perform as well several campaigns. So the thrust was measured with a thrust balance that was developed in place, and needed to be calibrated before in order to produce repeatable measures. But for us, what it was interesting as well, it was not only to measure the thrust of the I-25, but also to be able to measure several geometries and several roughnesses of the nozzle in order to see what was the optimal one and if it correlated to the simulation. So as you can see in the table, in the figure, nozzles which were unpolished or even calibrated orifices produced much lower values of thrust, which was as expected. And around the nominal point of operation, the thrust is about 0.2 or 0.22 millinewton of thrust. Actually. So as I commented before, the I-25 in its normal version, not in tilted one, it has flown last year on board of the SpaceTy Xionxiang 1.8. And you can see here in the figure the first functional tested performing on the thruster during the first firing and during the seal sublimation phase. So we have performed already several firings in space, and it's planned to perform on the spacecraft, which is placed on a near circular polar orbit, more firings in order to investigate the behavior of the system. But the first functional tested showed good performance of the thruster. So then the Montpellier Space Center has performed mission analysis in order to see if it was feasible to include the I-25 on board. So some parts of the mission analysis, which are on green, they are already done. Some parts are in process, and some parts need still to be done. But the main objective of this slide is to show that there are several elements which interact in this kind of simulation. So the ADCS, so the reaction wheels which need to compensate the torque produced by the thruster, the power needed so to optimize the solar panels pointing in order to obtain the maximum power possible for the operation. And these simulations take into account the several elements, performing thermal simulations with Thermica and other kind of simulations as well. So these are some results for some of the analysis. So this is a typical the typical target for performing firings during the orbit. So to align the thrust with the velocity vector, to perform firings during some time, and then to come back again for performing several future firings. So we can change around 1 kilometer with a 3U spacecraft on each of these firings. And basically the different images, so this shows that the pointing error is lower than 2 degrees for most of the mission profile, which is what was required. Only one of the reaction wheels for this analysis attains a velocity upper than 8,000 revolutions per minute, which is the maximum limit. But this is very good because this is before performing the optimization of this saturation requirement. So as I said, the Robusta, the analysis has shown that the I-25 was successfully integrated in its tilted configuration, and it will provide a thrust which is 0.2 millinewton with a total impulse of 75 newton seconds, which provides a versatile propulsion system for this small satellite mission. And the Robusta 3A mission will perform this meteorology and other kinds of measurements in order to improve the scientific data related to weather on orbit. So now the next steps are to integrate and to finalize the simulations and to continue the activities during launch to prepare for launch. So thank you very much for your attention, and if you have any questions, do not hesitate to contact me for further information.